So this work is a result of the collaboration with Tommaso and Torsten from ETH and David from Aachen University. So if I have to summarize this work in one sentence, I would say that this is a new algorithm for doing Allreduce, Allgather, and reduce scatter on multidimensional torus networks. So why specifically those three collectives? These are some of the most commonly used ones in deep learning training. And actually, even if in the paper we mostly focus on Torus, this algorithm we expect to provide advantages on any blocking network. So unless you have a non-blocking full bandwidth fat tree, we still expect this to provide some performance gain. But why Torus networks? And we have seen this a couple of times in the last 2 days. And the main reason is because of deep learning. So in distributed deep learning, you arrange parallelism in three different dimensions. So you have this data model and pipeline parallelism. And if you analyze the communication happening during this training, most of them happen between direct neighbors, which means that this communication nicely map to a 3D torus. This is just part of the story. In practice, some models also have some all-to-all communication, which means that in some case, a torus might be a little bit limiting. This is why there have been some more proposals for topologies which looks like a torus but have some extra links. So this is, for example, Hamming mesh, which is a torus with extra links so that you can reach distant nodes without having to cross the entire nodes on the same row or on the same column. And we have seen this a lot also in industry. So there was a nice talk by Google yesterday on TPUs. These TPUs are connected with some kind of a 3D torus, also with some extra link or at least like reconfigurable connection. And also like AWS and GraphCore are building chips arranged as 2D or 3D torus. So this is just to explain why we are interested in torus networks. It seems like something coming back from the 80s, but actually there are domains where this is really useful. And this is mostly for a cost reason. So rather than building a full bandwidth network, if you build a torus, you can save some money on the network. Now, before describing what Swing does, let me spend a few words on what's the state of the art for Allreduce algorithms on multidimensional torus networks. It's important to say that you cannot just take any existing algorithm and run on a torus because it will most likely perform very badly because the torus have a very low bisection bandwidth. So you need to have algorithms that are aware of that and schedule the communications in such a way that you don't have many flow collisions and so on and so forth. And there are mostly 3 existing algorithms for doing Allreduce on torus. I will just discuss here 2 of them. The third one you can find in the paper, and it's useful for some corner cases, let's say. So there are 3 main factors determining the performance of an Allreduce algorithm or a collective algorithm in general. The first one is how many steps the algorithm perform. So these algorithms perform a number of steps. At each step, they exchange data with some other node. The other one is whether or not they can use all the available network ports. So in this case, we are considering a setup where we have multi-ported torus network. It means that each node has one network port toward the north neighbor, south neighbor, east and west neighbors. So in a 2D torus, for example, you have 4 neighbors, 4 ports, 1 towards each neighbor. And the last point is about flow collisions. So on a torus, this is very likely. So you start here for flow collisions, we mean collisions between flows belonging to the same collective operation, not collisions between flows between different jobs or different users. So you have nodes communicating, very low bisection bandwidth, many flows collisions might happen. Okay, so the first algorithm is what is called bucket algorithm. This runs ring communications in each dimension separately. So you first communicate with all the nodes on the same row, then with all the nodes on the same column, and so on and so forth. Now, the issue with that is that you need to perform on each of these rings to complete, you need to perform a number of steps which is linear in the number of nodes that you have in each of the dimension of the torus, which for small messages, for small Allreduce, it's not gonna perform very well. But the good thing is that it can use all the network ports simultaneously. So what it does is that it takes your data, it split it into, I'm going to assume here a 2D torus. Then I will discuss about higher dimensional torus. It splits the data into 4 parts. It will run one Allreduce on each of these individual parts separately, and each of those will go into one of the different, into one of the 4 directions of the torus. And it doesn't have any flow collision because this is a ring. Anyone is just talking with its neighbor, so each link it's only used by one flow. So, and then we have recursive doubling. So recursive doubling is an algorithm which is logarithmic in the number of nodes. So it's much better when you have small Allreduce because you just have much fewer steps, especially on very large networks. But it can only use one network port at a time, which is kind of bad for larger Allreduce. And also it has many flow collision. I will gonna spend some minutes on that flow collision part in a few slides. So that's mainly the state of the art. There is a third algorithm, which is a traditional ring algorithm, where basically you have a big ring spanning all the nodes in the network. This is discussed in the paper. This is usually not performing very well, except that for some limited cases. So what about Swing? So Swing, it's logarithmic also in the number of nodes, like recursive doubling, but it can use all the network ports. So this helps a lot for larger messages. And it also has a few flow collisions. So it has fewer flow collision than recursive doubling, which it's enough to outperform both algorithms and the ring algorithm as well in most cases. So we will see this in the evaluation part. Now, I'm standing between you and the coffee break, so I'll try to describe the algorithm in the highest level and abstract way I can. Then you can find all the details in the paper. So let's start by discussing how, so this flow collision issue. And I'll do that by comparing side-to-side recursive doubling and Swing. And like we will just analyze what happens for the first 2 or 3 steps. So OK, let's start with recursive doubling. Let's suppose that we have a 1D torus, so basically a ring, with 16 nodes. In recursive doubling, in the first step, each node communicates with the node at distance 1. So 0 communicates with 1, 2 with 3, and so on and so forth. In Swing, first step, we do exactly the same. So far, so good. Now, step 2. Step 1. So it's the second step. It is called recursive doubling because the distance between communicating nodes doubles at every step. So now you communicate with the node at distance 2. And that's exactly the issue in the sense that here now we have some of the links which now are shared by 2 flows. So like both 0, the communication between 0 and 2 and the communication between 1 and 3 is happening on this link, which means that now all the nodes can only inject data at half of the bandwidth. So we're wasting some bandwidth here. OK. In Swing, we do something differently now. So we communicate with the other node at distance 1. So in this step, still, we don't have any congestion. Then step 2, the distance is doubled. So now you have one link which is shared by 4 flows. So each node now injects only at 1/4 of the injection bandwidth, which is bad. In Swing, we communicate with the node at distance 3. And we also do something different, which is, so in this case, you can see that you have a bunch of nodes all sending data in the same direction. So you have 4 nodes all sending data to the right. In Swing, we alternate those directions, basically. So you have links which are just shared by 2 flows at most. Now, you still have flow collisions, but like going at half the bandwidth is much better than going at 1/4 of the bandwidth. And we will see that eventually, this is already enough to catch up with the other algorithms in terms of bandwidth usage. Now, this proceeds for a number of steps. As you can imagine, now I'm explaining this in a very trivial way, but actually, we have to guarantee that the algorithm works. So this is a distributed algorithm. We need to guarantee that eventually everyone gets the correct data, that we are not missing anything, and so on and so forth. So this is a little bit more complicated to explain with slides. So I suggest you reading the paper for that. You will find the details. You will find how this generalizes to D dimensions. So we can run this on 5D, 6D, torus, whatever. And you will also find the correctness proof, which involves some math. But I don't want to shoot math at people before coffee break. So Okay, so that was the first intuition. The second one is how can we use all the network ports simultaneously? And for doing that, let's consider what happens in the first step. Okay, so in the first step, we say that each node communicates with the node at distance 1. Now, what we would like to do here is that we would like 0 to communicate at the same time both with 1, which is its right neighbor, with 3, which is its left neighbor, with 12, which is its north neighbor, and with 4, which is its south neighbor. So we take the data, we split it into 4 parts, and we run 4 independent Allreduce on each of these 4 parts. We run exactly the same algorithm. Okay, so this is to use the first port. To use the second port, we consider a logically transposed torus. So we are not going to actually to transpose the physical connection of the torus. It's just that logically, we assume that we inverted the rows with the columns. So now our right neighbor will be node 4. So we are using also the other port. How to use the remaining 2 ports? We shift the columns by 1. So we consider, let's say, a rotated torus, so that now 0 will communicate with this, its left neighbor, which is 3. And then we combine transposition and shift of the torus. So by applying this, I mean, this is just logically rearranging the node IDs in such a way that eventually we can communicate with everyone. So in these 4 communications happens at the same time, so we're using all the links and all the ports on the network. Okay, so these were the 2 main intuitions, reducing the number of flow collisions and using all the network ports. Now, as you can see here, what we would expect is that this would outperform the other 2 algorithms, actually the other 3, I didn't show the other one, for almost all the cases, except that for very, very large Allreduce. So for very large Allreduce, you will have that these few flow collisions will still have a performance impact, and we will see this in the evaluation. Okay. So what's the evaluation setup? We run simulations on top of the SST packet level simulators. We simulated data center networks with 400 gigabit per second links and 100 nanosecond link latency. So we then also analyzed for different parameters for bandwidth and latency. And we simulated a per hop latency of 300 nanoseconds to cross any single switch. So just for the sake of brevity, I'm not going to show all the single lines for each of the algorithms. I'm just going to show the relative improvement of swing compared to the best state-of-the-art algorithm. So for each message size, we take the best performing state-of-the-art algorithm, we take swing, and we show the ratio between the 2, basically. So if we are on the green area, swing is outperforming state-of-the-art. In the red area, swing is being outperformed by state-of-the-art. Okay, so let's start with 8x8 torus. So we can see this kind of bell-shaped curve, which was actually what we were expecting. So in the paper, you also find some theoretical modeling. So what's the model behind that? So what we can expect. And we expect exactly that. So the largest advantages in the medium size Allreduce range. So in this case, for between like 2 kilobytes and 2 megabytes, more or less. So on this first part here, we outperform the recursive doubling because we are communicating with nodes at shorter distance, so we need to cross fewer links. Here on this part here on the right, we are being outperformed by bucket because we have still a few flow collisions, and for very, very large messages, this is gonna have an impact. Now, I need to say that in practice, in many, many cases, you don't run such large Allreduce. So you don't run like 500 megabytes Allreduce. You split it into smaller ones to better overlap communication with computation. So usually you just don't run such a big Allreduce all at once. Then what happens when you increase the number of nodes? We still observe the same trend. In general, we can see that the maximum positive gain increases, and this is because the network is getting larger. So this number of steps that you perform in the ring is getting bigger, and it's gonna have a higher cost. At the same time, we are dropping a little bit more here. This is for the same reason. The network is getting larger, so eventually these flow collisions, this means that there will be communications happening between very distant nodes, so we will have many flow collisions, and this is why this is also dropping. So we tested it up to 16K nodes. We observed the largest negative gain of 22% for very large Allreduce. Now, it's important to say that this is, we proved in the paper that actually this is kind of the lower bound. So this doesn't get worse than that. And in the best case, a maximum gain of around 120%. So now, in the paper, you will find many more results. So let me just go quickly through some of those. So how do we read this plot? So we have these box plots here. Each box plot is the distribution of one of these curves here. So for example, the purple curve is this box here. So each point is one of these message sizes. So we show basically the distribution of the performance advantages over all the message sizes. OK, so this is what we just showed. Then we try to see what happens when we increase the network bandwidth. So network bandwidth is increasing year after year. Is this still going to be relevant, or eventually this doesn't matter anymore? And the answer is that this is going to be even more relevant for higher bandwidth, because the higher the bandwidth, the higher will be the relative weight of the number of steps on the overall performance. Which means that if you have a very, very high bandwidth, eventually you don't really care whether you have flow collisions or not, because anyway, the bandwidth is so big. What do you care? It's how many steps do you perform. And performing a logarithmic number of steps is going to help. So for higher bandwidth, eventually, we don't have any performance degradation compared to state of the art. So we were able to outperform all the algorithms, regardless of the message size. This is the case also for higher dimensional torus. So if we move to 3D and 4D torus, this is also what happens. Why? Because the more dimensions you have, the more, the lower the network diameter will be, which means that eventually most communications happen between nodes that are not so distant. So the impact of flow collision, again, is going to be negligible. So for 3D and 4D torus already, we don't observe any performance degradation regardless of the message size. So torus-like network. So I mentioned Hamming mesh at the beginning. So these are torus with extra links. And now the key intuition here is that those extra links help in alleviating congestion, so in alleviating collision. So you have some extra links. So these collisions now get distributed towards those extra links. And eventually, again, you don't get any performance drop. So having those extra links alleviate this flow collisions issue. And then there are also some results for rectangular torus. This is a little bit more complicated to explain. So what if you don't have a perfectly shaped, square-shaped torus? This is still going to work. We observe some outliers both in the positive and negative side. And there are reasons for that, which I will be happy to talk offline. So to conclude, so for each of these blocks, you will find the detailed analysis in the paper. So you will actually find the actual line for each of those algorithms. Okay, so you basically the expanded version of each of those boxes. So to conclude, in this work we presented Swing, which is an algorithm for doing Allreduce, reduce scatter, and all gather on multidimensional torus networks. We have seen that this is based mostly on two intuitions. One is to reduce the number of flow collisions by reducing the distance between communicating nodes. The other one is to use all the network ports by considering this translated and rotated version of the torus. And we analyzed this on a wide set of different scenarios for different bandwidth, different topologies, and so on and so forth. And with this, I conclude, and I will be happy to take any question.